Hello everyone, welcome back to another lecture of COP-3402. Today we're going to be reviewing how to compile arithmetic operations in your simple IR code to arithmetic operations in assembly code. And at the end of the lecture we'll be reviewing how to get started with the compiler project itself. So to begin, let's just review arithmetic in simple IR and assembly. The big idea of what we're going to be doing is translating instructions like this, x equals a plus b, into assembly instructions of this form, add rbx and rax together. And there's going to be more instructions involved in the compilation here, and we'll see that in the following slides. So some of the challenges with doing this is that we have to be able to handle arithmetic operations involving variables, integer constants, and also performing assignment, because in our simple IR grammar, we can only have an arithmetic operation when there is an assignment on the left-hand side. So when the result of the operation is being assigned to a variable. And you can see this in this grammar here. So we're always going to have a name on the left-hand side, some equal sign here. These quotes mean a string literal. And the right-hand side is going to be either a variable name or a number as the first operand, then one of these operators as the operator between the operands, and then a variable name or a number as the right operand of the arithmetic expression. So our big idea is that we're just going to look at this as a sort of a template that we're plugging values into or extracting values from. There's going to be always a name on the left-hand side, some operand on the left, some operand on the right, which can either be a name or a number, and then some operator between them. And again, variations here, the operands can be integers or they can be names, and we have all these different operators we need to support. So let's look at how we can handle variables first. Well, you might recall from the previous lecture that we have this data structure in memory when we're working with our compiler called a symbol table, which stores the offset from the base pointer from the stack frame at which each variable lies in memory. So because the absolute addresses of these variables cannot be known at runtime, we store offsets from the stack frame for each variable so we can access their locations at runtime. So for instance here, if we have a variable x, a, and b, they would be at the following offsets. These are all local variables. They're at negative offsets because the local variables grow downwards in the stack. So how can we actually access these operands? Well, you might recall from the previous lecture we saw that the variables are stored as offsets from the RBP array, which is not really an array, just a register. And you can think of it like an array where we're accessing values from it at different offsets. So for example here, if we were to write this as C code, we would say to get the value in RBP, oops, there's a typo there. That should not be RPB, it should be RBP. To get the value of A from RBP, from the RBP array, we would use offset -24. You could look at it like this if we were writing C code, and just to refresh you, this is because the value A here was at offset -24. So in this example, we would use -24 for the offset to get the value of A. And in the assembly code, the syntax is slightly different. We list the offset first, then in parentheses, the base address that we're getting the offset from. So these are basically equivalent assembly to C, like a one-to-one mapping. So the way we can actually extract values from these variables where they reside in memory into registers is to use these move instructions like this, where we're moving the values from offset -24 from the stack frame from the base pointer into the RAX register here. So remember, in the AT&T syntax of assembly that we're going to be using, the destination register is always on the right. So how can we represent integer constants? Well, we just prefix their values with a $sign. So assembly supports moving from integer constants. These are immediate moves. And we just put a $sign before the value that we're going to be moving. So for example, if we want to move the value 1 into the RBX register, we would just say move $1 and then %RBX. So how can we actually assign two variables? Well, the RBP again holds variable addresses, as we've seen before. We just make the variable address itself the destination of the move. So we can actually move directly from a register value into an address here, or an offset from the base pointer from the stack frame here. So assuming the variable b is at offset negative 32, then we just assign, we just move from the RX value into negative 32 offset from RBP to actually assign the RX value into variable b. So how can we actually perform arithmetic? Well, let's look at addition as a simple example because many of these are going to follow a pattern. We'll start with just addition because it's the simplest. If we want to add the RBX register into the RAX register and store the result into RAX, we just write it out like this. So again, RAX equals RAX plus RBX. You can kind of think of it as going in sort of reverse. So we're going left, right, right, left. So RAX equals RAX plus RBX. And one thing I want to point out is that because addition is commutative, you could have put this in any order. Actually, this is sort of incorrect. If we swap the order here, RBX would have been what we were assigning to instead. But the result of the addition would be the same because addition is commutative. Now contrast this with subtraction, which is not commutative, so the order of the operands is important. Now we have to make sure that we are putting our source and destination operands in the correct positions. So in this case, we're saying RAX equals RAX minus RBX. So quick quiz, just to test your knowledge of how this actually works. What are the results of these additions? Well, for this one, RAX plus RBX, we would say RBX equals RBX plus RAX. So the RBX register would be equal to 14. And if we're looking at the value of RAX, then it would just be 9 because we're not storing anything in the RAX register here. And then in this case, where the RAX is the second value, the value in the RAX register after this addition would be RAX equals RAX plus RBX. It would be 14 as well. But with subtraction, it's different. So if we were to say, let's just look at the result of the subtraction here, regardless of what register we're storing it in. This would say RBX equals RBX minus RAX. RBX is 5, RAX is 9, 5 minus 9 is negative 4, so the result of this subtraction would be negative 4. On the other hand, if we were to put RAX second, then the result would be RAX 9 minus RBX 5 is 4, and we store the result in RAX. So this would be 4, this would be negative 4 at the top. Multiplication is pretty simple. It's also commutative. It's just like addition. So if you know how to do addition, you can do the same thing for multiplication. Now, how can we actually translate some of these examples to assembly? Let's look at a bigger example. So we have a equals 9, b equals 5, x equals a plus b. Let's assume we have these offsets. X is negative 16, a is negative 24, and b is negative 32. The big idea of what we're going to be doing here is loading the value in the variables into registers, performing arithmetic using those registers, and then storing the result of the arithmetic back into the variable x. So the assembly code would be this first part here. We are moving out of the value, the place in memory where the a value is stored into the RAX register. We're moving the value out of the place in memory where the b memory value is stored into the RBX register. So now RAX contains the value of A, RBX contains the value of B. Then we're actually performing the addition, so we're saying RAX equals RAX plus RBX. So this is like saying A equals A plus B. And then we're moving the value in the RAX register back into the memory address, the value of the memory address where X is stored. So X is negative 16 offset from the stack frame. So we're moving RAX into that location of memory. So this is like saying x is equal to a, essentially. Now for integer constants, it's going to be a little bit simpler. We only have to move one variable value. So that's the, well, we have to move both, I guess. But the only value we're moving into RAX here is the immediate value, 7. Was it 7 or negative 7? So it's 7. So there seems to be some sort of typo here. It should be 7. Then we're moving the value b into RBX, so we're saying negative 32, offset from RBP to get the value of b. We're moving that into RBX, and then we're adding RAX to RBX and storing the result in RAX. This is actually performing the addition. And finally, we're storing the result in X. So we're saying now that RAX has the result of the addition here, we're moving the value from RAX then into negative 16 RBP. And could you write this in a simpler way? Maybe you could use fewer registers. But the big idea is that if we always follow this template here, this pattern of moving our values into registers first, and then performing the arithmetic, and then storing the result in the destination variable, we have a template that we can follow for every single case of arithmetic operations, and our compiler will be easier to write this way. So that's why we follow this template all the time, even though you probably could have just put $7 right here immediately, or maybe right here I should say immediately. You could have omitted fewer instructions to accomplish the same goal. We're always going to follow this template because it lets our compiler be simpler to write. And the big idea here, I'm going to zoom out a little bit so you can see this whole slide, is that we're just following this template. You can kind of see it at the bottom here. Just two move instructions, the appropriate operation, and the appropriate move instruction to move the result into the destination variable. Now this works for most of the operations, but there is an exception here that I want to show next, because there's always an exception, you know. Division. Division is going to be a little bit different. Division and remainder. They're going to be a little bit different from add, subtract, and multiply. So integer division, maybe I'm not sure, let me see, where should I mention this? I guess I'll mention it here. The thing with integer division is that the x86-64 instruction set specifies that for us, division, the numerator can be up to 4 words long, and for us, one word is 32 bits. That's 128 bits long. 128 bits long. But the denominator can only be 64 bits, and making things even more complex, the maximum register size is only 64 bits. So our numerator needs to be 128 bits long, but the max register size is only 64 bits, so how can we actually accomplish division? Well, the way we do this is to first move the value we want into the numerator. So we're moving the 64-bit value up to 64-bit value that we want to divide by, in this case just the literal 9. This could be a variable though if we use an offset from memory, into the RAX register. Then we're moving the value 5 into the RBX register to set up our denominator. And we're using this operation CDQ, which stands for convert double to quad, to convert our numerator into a 128-bit register. So remember, these register values, RAX in this case, can only be 64 bits at most. That's 2 words, because a word is 32 bits. But integer division for x86-64, which we're translating our simple IR code to the assembly version of, requires that the numerator be 128 bits. 128 is 4 times 32, so it's a quad word. Quad meaning 4. So to convert our double word, RAX, 64 bits, into a quad word, we use this instruction CDQ. So this converts RDX, RAX together into one single 128-bit pseudo-register, basically. So we're really combining both RDX and RAX in here, but as long as our RDX register is just not set, this won't be affecting us at all, so it's really just RAX. Now, we actually perform the division, so here we call the IDiv instruction, and all we have to pass to it is the 64-bit or double word value of we want to divide our numerator by. So we already had set up RBX here with the value 5, so we just pass RBX to the IDiv instruction here, and this will divide our pseudo 128-bit register here by RBX. And afterwards, the result is actually placed in RAX, and the remainder is placed in RDX, which means we can use the same operation, this template here, for both division and modulo. So yeah, we can use, like it says here in the notes, used IDIV for division and modulo, set up the predefined registers first, REX and RDX, and retrieve the results from predefined registers afterwards. So if we're doing division, we'll want to use REX. If we're doing remainder, we want to extract the value from RDX. And just as an example, a equals 9, b equals 5, x equals a divided by b. The assembly code would be to move the value from a, we're dividing by a, right? Yep, so move the value of a into RAX, move the value from b into RBX, perform the CDQ operation to convert our double word register RAX into a quad word register for division, and then perform the IDIV instruction to divide our 128-bit pseudo register that we get from or by the value of RBX. And then we get the result by moving out of the RAX register, which stores the result of division, into the memory offset at which the x variable lies. And then again, how would the assembly code change our modulo? Well, all we would do differently is we would move out of the RDX register. So I think this shows it here. Yeah, just move out of the RDX register. D for remainder, I guess. That's maybe one way to remember it. Okay, so that's it for arithmetic operations. I hope that wasn't too much at once. I recommend reviewing the notes if you want to, or really I'd recommend reviewing the notes just to polish your skills with this. A bit of repetition, you should be fine. Now I want to go on to talking about the project and at least show you how to get started, because this one is going to be a longer project that we're going to be focusing on for the remainder of the semester. So the CodeGen project is, the big idea of it is that you're writing a compiler to translate simple IR code to AT&T Intel x86-64 assembly. So to get set up, you'll want to run some instructions here to set up your Git repo for submission. I'm going to skip these instructions for this example, but I do want to show you how to actually get started with the code. So I'm going to copy these instructions here to download the starter code, unpack the starter code, and then create my file for modification for actually writing code. So I'm going to copy this, then go to my terminal window I have here. In my current directory, I have nothing on my desktop, so I'm going to make a directory for this project. CodeGen1. Oops, I have a typo. Here, let me move my mic. All right, so now I'm going to create my directory again, fixing that typo. Going to cd into it. Now I'm going to copy this code to download the starter code for the compiler project. You can see it's here. I'm going to unpack this code. So now the starter code is in my current working directory. And I'm going to run this instruction here to move my template code into the codegen.cpp file, rename the template file into the codegen.cpp file. And this codegen.cpp file is going to be the file that you'll be working with for the project. So you're going to be defining all your functions in here. And the way this file is structured is that you can see there are all these enter operations, enter functions, I should say. And these are the ones you're going to be filling in for the project. What each of these do is they define a different way to visit or perform an action on each one of the different AST nodes in the parsed simple IR code that you're going to be having access to from Antler. So we're using this Antler 4 library. It's in the readings. I recommend reading up about it to parse our simple IR input. And then you're going to be defining these functions to define semantic actions to perform when you visit each one of the different kind of abstract syntax tree nodes in the parsed Antler input. So what does this mean for you actually writing code? So for you, what you'll want to do is first look at the project requirements. So every one of these CodeGen parts, there's going to be 3 parts to this assignment. We're on the first one now. Each part is going to give you some functions that you have to define yourself, and possibly some hard-coded functions that you'll be given hard-coded definitions for testing. So first, let's look at the ones given to us. In this case, enter unit, enter local variables, and enter assign. I'm not really going to explain these too much, but for this project, you'll just want to copy in these 3. So I'm going to copy in enter unit, next enter local variables, And what this actually does is set up the symbol table for you. So this is a bit trickier code, so that's why we give it to you without you having to implement it yourself. And then enter assign. And enter assign is honestly one of the simpler functions here. I think if you want to get an idea of how these listener visitor functions work, I would recommend reading the definition of enter assign. And one more thing I want to mention is that you can see we have these fields here, context.operand, context operand, for example, context variable. These come from directly the ANTLR grammar. So if I open a new tab here, and I open the simpleir.g4 file, you can see in the enter assign we have this operand that we're accessing, this operand field. And that comes directly from the grammar. So you can see in the grammar we have this operand field for an assign statement, or a production, I should say. And an assign is either a name or a number. That is how we get this operand field from the context parameter here, which is a type of assign context. Similarly, we also have this variable field here in the assign production. That's where we get the variable field from in our, or what it refers to in the assign context here. And then getText actually gets the actual parsed text behind this variable name. Okay, so with that we have all our definitions. Let's proceed to some testing. So first I'm going to try and just make this file, try and just compile it. And it works, so it's compiling now. That's good. And all the libraries will be set up for you on Eustace. So I've installed them on my own machine, but you don't have to install them on your machine. They'll be pre-installed for you on Eustace. And now if I were to run this code on some example input, let's say right here, I'm going to say CodeGen, and then I'm just going to paste in this input and then EOF. You can see it actually generates some assembly code, so it seems to be working. However, one problem is that this is not enough to actually execute. So this code does not actually, will not actually be runnable. So how can we fix this? Because we need to actually run your code for testing. The way to do this is the way we do this is to give you hard-coded listener functions. So the reason why we give you these hard-coded functions is because a compiler, normally, you can't really test it until everything works. Because you can't, you can't really test something until the whole compiler just already translates code that actually can be run. But to solve this problem, because we want to give you the compiler project in pieces, so you only have to implement pieces at a time to make it easier for you, we give you some hard-coded functions that will not work for every possible input, but will work for the inputs we'll give you for testing. That way you can only have to implement small parts of your compiler at a time. So for CodeGen 1, we're giving you these examples here, these hard-coded functions here. So enter function we'll give you first. Let me take a look back, go back to that. Oops. So I'm just going to try and show you how you can use these hard-coded functions to test your own code. So first I'm going to copy and paste all these definitions in. Enter function. Oops. There we go. Enter end. That's the next one. Enter parameters. Actually is empty, so I'm just not going to copy it. Enter return. And finally, enter call. So if you use these hard-coded definitions for these functions, then you will actually be able to, I think you should put these in. You will actually be able to translate inputs that follow this template. So I'm going to copy and paste this template here. Actually, there's some instructions here to do this. We're giving you a template, and we're also giving you this iolib.c file, which you can compile to gain access to these printint and readint functions. And you can actually use these directly from within your own simpleIR code, because we're translating to assembly, and assembly can be linked with C projects, C code when it's also compiled. You're actually able to gain access to these C code functions from directly within your simpleIR code, which is kind of cool. So what we're going to do is just run these 2 lines of code here to download these files. And now we're going to actually run our CodeGen. Actually, let's run make first to recompile it. Now we'll run our CodeGen to compile our template file to template.s. You can see it worked. Here's our assembly code, and this is a full, not quite a full executable, but it's enough to where if we link it with the other, with GCC here, we can make it an executable. So we'll run GCC on this and link it with our iolib.c file that we downloaded to gain access to printint and readint. And now we can actually run our template code. And you can see it prints 0. And that's because in this template code up here, we call printint result, and result is initialized to 0 by default. So for you, for testing, you can actually change the values of some of these variables. Just modify the template IR function and make sure, just don't change any lines that say do not change. That should be intuitive, hopefully. But you can add any of your own code you want here. So for instance, let's say we want to change the value of result. And we can do this because we already implemented the enter assign operation with some of those copy and pasted code examples we give you for this project. I'll say result equals 42, a famous number in programming and in literature. Maybe not literature, but novels at least. I'll save and quit this, and now we can actually run CodeGen again to compile this code to assembly, run GCC to compile that assembly code with our iolib.c file to an ELF executable, and then we can run that template code, and now we print out 42 because this template stores its result in, or stores 42 in result, and then we call printint to print the value of the result. So I recommend testing your compiler by creating multiple of these template files and just maybe setting up a make test rule or something to run tests on all of them. If you do set up a make test rule, I will say don't put test as the first instruction in your make file, because that will change the default rule for your make file to run test, which is not what you want. That would break the grading script. So if you're going to make a test rule, put it towards the end, and you could say things like, I don't know, CodeGen. You would basically just copy and paste the lines here to run your code. So I could say something like this. And you probably want to use variables and whatnot to make this a bit nicer. Maybe make this depend on CodeGen, that way your test rule will compile it. And of course, you'll want to add that to your phony targets. And now if I run make test, you can see it actually runs the test automatically for me. So I could actually run, if I wanted to, I could put multiple, oops, let me open the make file again. I could put multiple different files here and run them all and check all their outputs. There's, you could like make your own tests basically to make sure your code works before you submit it. And I think we give you some of the test cases down here, at least descriptions of them. Or maybe, oh wait, that was a different file. Here we go. Yeah, here's the test cases. So you can like test most of these out. I think we give you public test cases for these ones. Yeah, you can see right here, CodeGen test. We give you the even number test cases, or odd number test cases. But you can implement your own tests for the even numbered ones if you want to be sure that it's correct. All right, so that wraps up this lecture. Good luck. I think this project's going to be hopefully fun if you like programming, if you like tinkering, if you like making up systems, which a lot of programmers do. You should really enjoy this project. Compilers are one of the most fun things for programmers to build. There's a saying that if you leave programmers alone long enough, they build video games and programming languages. So hopefully this will help cultivate a sense of excitement for you for building complex systems. And if not, at least now you've learned about one thing in programming that you don't like doing. So you can maybe work on some other area of programming like database development or web development or graphics or something like that. All right, good luck, and I'll see you all next time.